Welcome everyone to this session. So we'll be discussing some topics from Module 4, chronic penney model and zone folding. In the last session, we discussed what a superlattice is. A superlattice is a quantum well which is having barrier thickness very thin so that the electrons can tunnel from potential well to the barrier. Now, when we consider a superlattice, we can study the band structure from the point of view of two approximations. One is Cronin-Penney model, the other is tight binding approximation. So before that, we are assuming the superlattice, or we are considering the superlattice to a crystal lattice and the quantum wells inside it to atomic potentials in a crystal. So it was in 1931 that Kronig and Penney established a model for solids in which the periodic potential seen by electrons was precisely that of a square shape for a superlattice potential, which means in a superlattice we are considering a periodic potential and a square shaped potential well. Now, so in this 1D potential, D is the periodicity of the potential superlattice and D is equal to A plus B, where A is the thickness of the barrier, thickness of the well, and B is the thickness of the barrier. Now, we are considering the superlattice to be a collection of multiple quantum wells. So, the barriers are thin and electrons can tunnel through the barriers, which means there is a presence of electron inside the well as well as in the barrier. So, as you all know that electrons have dual nature property, which means electrons can behave as as wave functions and as particles. Right. So, we'll have wave functions both inside the quantum well and also in the barrier. That is one thing which is to be noted here. Another thing is we are keeping the superlattice in the z-axis, right? So 0 to A lies in the positive z-axis, which means the thickness of the potential well, and the thickness of the barrier 0 to B lies in the negative z-axis, so that's minus B. Okay. Another thing to be noted here is inside the well the potential is 0, but outside the well, that means in the barrier there is a potential and that potential will be equal to the barrier height V0. Right. So keeping all these in mind, we go to the derivation for Cronin-Penney model of a superlattice. In the well region, as said, 0 less than A, potential is 0, and the wave function can be represented as phi of z is equal to A e raised to I k naught z plus B e raised to minus I k naught z. This equation, equation number 1, is actually a solution to Schrodinger's wave equation for an electron in the potential well, 1D potential well, which we have already covered in the first module. So I'm not going into the Schrodinger's equation or derivation. It is equation number 1 is the solution for the Schrodinger's wave equation. And k naught square, k naught is a wave vector where k naught square is equal to 2me by h bar square. Now, taking the first derivative of equation number 1, Dou phi by dou z is equal to I k naught a e raised to I k naught z minus b e raised to I k naught z. So let it be equation number 2. So we have first we wrote the equation for wave function, which is equation number 1, solution to the equation, and then we are taking the derivative, which is equation number 2. Now for the next wave, which is there in the barrier, which means due to tunneling, the wave function extends into the energy barrier of height V naught and thickness is V. So in the barrier, which is minus B less than Z less than 0, we can see that similarly when we apply the Schrodinger's wave equation, we get the solution as phi of z is equal to c raised to qz plus d raised to minus qz. C and D are coefficients just like A and B, and q is a wave vector, and q square will be equal to 2m by h bar square v naught minus e. And from this, we can write V naught minus E, the relationship between wave vector and energy, as V naught minus E is equal to h bar square q square by 2m. Right. So in the first equation, we are considering that the potential is 0. So there is no term here in the wave vector. But here, since we are considering the wave in the barrier, and since there is a potential barrier, we have to consider the potential, which will be V naught minus E, right? So we are considering the V naught term here, right? So that comes to equation number 3, and we're taking the first derivative. So d phi by dz is equal to q into c raised to q z minus d e raised to minus q z. That is equation number 4. Now, the next condition is, we are considering that both the wave functions and their derivatives are continuous at z equal to 0 and z equal to a. Then what happens? Suppose, so in the first equation, we substitute z equal to 0. What we will get is psi of 0 is equal to a plus b. And in the second wave equation, if we substitute z equal to 0, we will get psi of 0 is equal to c plus d. Since the LHS are same, a plus b equal to c plus d. And this is equation number 5, which means we are considering the wave functions are continuous at the boundaries z equal to 0 and z equal to a. Now, it's not only the wave functions, the derivatives of the wave functions are also continuous. So from equation number 3, equation number 2 and equation number 4, we finalize similar to what we have done just before. I k naught a minus b is equal to q into c minus d, and let it be equation number 6. Now we are applying a theorem which is called the Bloch theorem. The Bloch theorem can relate the wave functions at two different locations by psi of a is equal to psi of minus b e raised to I k a plus b, where psi of a and psi of b are two different wave functions. And k is a wave vector which corresponds to the Bloch wave functions. Right. So by applying the Bloch theorem into the equations corresponding to the well and the barrier regions, what we get is a plus b, which we have found here, right? A plus b, equation number 5. From here we get a plus a e raised to I k naught plus b e raised to I k naught is equal to c raised to I qb plus d e raised to qb into the whole bracket e raised to I k naught a plus b. Similarly, from equation number 6, when we apply Bloch wave function into equation number 6, what we get is this equation number 8. I k naught a e raised to I k naught a minus b e raised to minus I k naught a is equal to q into c e raised to whole bracket c raised to minus qb minus d into e raised to qb into e raised to I k naught a plus b. Right. Now we got a set of 4 equations. A plus b is equal to c plus d. As you can read, the first 2 equations are uh, by applying the boundary conditions, and the next 2 are by applying the Bloch-Wade theorem. Right. So we get a set of 4 equations, and we can write it into the matrix form by taking the coefficients like this. Right. A, B, C, D equal to 0. This coefficients multiplied by A, B, C, D equal to 0. Now, the above equations will have a solution if the determinant of the coefficient is equal to 0, which means the equation can have a non-trivial solution when the determinant is equal to 0. So, after expansion of the determinant and after simplifying it, we get the determinant in terms of a equation which is equation number 9. Right. Here q and k naught are wave vectors. A and B are, A is the thickness of the well and B is the thickness of the barrier. Now suppose we assume a case where A equal to B and the effective mass of electron is same as in the well and also in the barrier. And for the particular case of material which you are choosing as gallium arsenide and aluminum gallium arsenide, and when energy is less than the barrier height E less than B naught, we can get a graph for energy band diagram. We can get an energy band diagram like this by simplification and by doing some particular calculations on equation number 5, keeping in mind that A equal to B and using all these conditions, we get a energy band diagram like this. Okay, so this graph gives the superlattice with band discontinuity of 0.3 electron volt and Me star is equal to 0.067 M naught. Now the left hand side means the y-axis shows the edges of band and x-axis shows the thickness of the barrier. What is inferred from this graph is that this graph is actually plotted from this equation, right? Okay, so what exactly we find from the graph is that for values larger than 10 nanometer, electron energies are well defined and it corresponds to individual quantum wells. Means we can see discrete energy levels here after 10 nanometer. Means it behaves as a it behaves as a quantum well. Now, when the barrier is smaller than 6 nanometer, we can see the energy levels, discrete energy levels will form bands and band gaps. Means allowed bands and forbidden bands. Right. So then it becomes a super lattice. That means the thickness, as the thickness is greater than 10 nanometer, we can see discrete energy levels and that becomes a quantum well. And the thickness of the barrier is less than 6 nanometers. We can see that the discrete energy level merges to form forbidden and allowed energy bands. Right. So that is the inference from the graph, and this graph is plotted by making some approximations in this equation. Now, moving on. Another concept which we are discussing here is nearly free electron model. So actually this is a model which is used for bulk lattice that is applied to crystal. So, but we are assuming that we are considering the superlattice similar to a crystal in which quantum wells in the superlattice are considered as atomic potentials in a crystal. So, in such a model, NFE model, when it is applied to a crystal, it is assumed that the electrons are subjected to periodic potential inside them. And due to this periodic potential, we are able to see forbidden bands and allowed bands. Right. So, and due to the periodic potential, there will be discontinuities in the energy values whenever K, which is a Brillouin zone, which is equal to n pi by A. Which means we are plotting this graph. We are taking the EK graph, energy with respect to K vector, K wave vector of a crystal lattice. And this graph is called a extended zone representation. And what we see from this graph is actually this graph should be this dotted line shows the graph for a free electron parabola. And this free electron parabola breaks into several bands and gaps at the edges of the Brillouin zone. K is equal to n pi by A. That means you can see these bands, these dark lines are the bands. But at pi by A, at 2 pi by A, and similarly at minus pi by A, minus 2 by A, you can see that there is a gap, right? There is a gap here, band, and there is a gap, there is a band, gap. So these gaps are occurring exactly at regions of n pi by A, where n can be, n starts from 1, 2, 3, etc. like that. Right. So both in the positive axis and also in the negative axis. So the breaking occurs at the Brillouin zones, where K is the Brillouin zone, where K is equal to n pi by A. This is a case for a crystal. Now applying the same theorem to a superlattice, what happens? K is equal to n pi by D, plus or minus n pi by D. At pi by D, 2 pi by D, 3 pi by D, etc. You're seeing gap. Right. So instead of getting a free electron parabola, you're having bands as well as gaps. And these gaps are occurring exactly at n plus or minus n pi by D or the Brillouin zones. And in the case of superlattice, since that D, which is the periodicity of the superlattice, is much greater than A, we can say that these bands are mini bands and the gaps are called mini gaps. So mini band, mini gap, mini band, mini gap, just like that. Okay, so now this is the extended band diagram, figure A, and figure B is the diagram for first Brillouin zone. Another concept which I'm going to discuss here is the zone folding. So the portions of the band can be translated to reduced zone minus pi by t less than or equal to plus pi by t. Like it is as if that the superlattice potential folds the quasi-free energy band of a solid into the center of the reduced zone if we make representations in the first Brillouin zone. So what does that mean? It means that suppose you're considering you have drawn this diagram into another paper and you're folding it these lines. Okay, these are these small dotted lines, and you're folding the paper in such a way that, so this is a parabola 0 minus pi by t, 0 pi by d. First Brillouin zone will be a simple small parabola, and when you fold exactly at pi by d and minus pi by d, what happens? The next Brillouin zone, which is occurring at 2 pi by d, folds and merges exactly with the first Brillouin zone. Right. So first Brillouin zone is considered as the base, and this next Brillouin zone means the Brillouin zone at 2 pi by d will fold and merge into the first Brillouin zone. Similarly, the Brillouin zone at 3 pi by d, if it is folded once, it will merge with the Brillouin zone of 2 pi by d, and if it is folded twice, it will merge with the first Brillouin zone. Right. So this concept is called zone folding. That is, it is as if that the superlattice potential folds the quasi-free energy band of a solid into the center of the reduced zone if we make representations in the first Brillouin zone. That is the concept. Now, the zone folding can be typically seen in superlattice, and it has important consequences in the direct and indirect characteristics of a semiconductor structure. Right.